Welcome back everyone. My name is Pedram and this is where we do machine learning codes and concepts. Let's get started. Welcome back everyone. In the previous module, we introduced logistic regression as our first machine learning model for classification tasks. Now in module 7, part 2, we will explore evaluation metrics that can be used to measure the performance of classification models in general. So while there are many potential evaluation metrics out there, the most appropriate ones to use will depend on some factors like data structure and class distribution. So for example, if the classification data is very imbalanced or balanced. So we'll cover the most common metrics, discuss their strengths and weaknesses, and we'll talk about when certain metrics are preferable over the others. So by the end of this module, you will have a solid understanding of how to critically evaluate classification models by choosing suitable and right evaluation metrics for your specific task and dataset. So with this knowledge, you'll be equipped to thoughtfully select metrics and interpret results as you build and refine classifiers. So without further ado, let's jump into it. All right, so these are the metrics that you're going to cover in this video. So if you watched the previous video, you already should know that what is a confusion matrix. And based on this simple confusion matrix, we can go ahead and define multiple different performance metrics as well, right? So this is our simple table, let me actually highlight it. So this is our 2x2 confusion matrix. So it means that we're dealing with a two-class classification. We can have three-class classification confusion matrix, multiple class classification, and etc., right? But based on that simple table, we can extract these informations. So we can talk about accuracy, precision, recall, F1 score, MCC, ROC, and AUC. So these are the most commonly used one, but this is the metrics are not limited to this one. So let's cover them. Okay, at the heart of every performance metrics that we're going to explore, there's something called confusion matrix. Confusion matrix summarizes how successful the classification model is at predicting examples belonging to various classes. At the end of the day, for example, if you have two classes, we're going to care about four numbers: true positive, true negative, false positive, and false negative, right? And all the other performance metrics are built upon based on these four numbers for two-class classification. And the statistics are easily generalizable to models with more than two classes, let's say three classes, four classes. So let's start with confusion matrix for two-class classification. All right, we are going to have two classes, 0, 1, right? Let's call the zeros negative and ones positive. Well, this is what the data actually represents. So this is our y. The target variable, the actual, can be either 1 or 0. And this is what the model predicts. This is what we get out of our f hat, right? So the model can predict either 0 or 1, right? So if in reality the actual is 1 and the model is predicting that number correctly, so this is true positive. This is a good number. So actually it is 1, the model is predicting 1. If actually the observation is 0 and the model is also predicting it 0, this is a good number too. So this is true negative. So true positive and true negatives are good numbers. We want to maximize them. On the other hand, we have some errors, right? What are the misclassifications? Let's label them. So I'm going to use red. So if in reality the actual value is 1, but the model is falsely predicting it to be 0, so this is our false negative, right? This is a bad number. And lastly, if in reality the observation is 0 and the model is predicting falsely 1, then this is what we call false positive. So as you can guess, false positive, false negative, these are bad numbers. We want to minimize them as much as possible. And true negative, true positive are good number, and we hope that the model that we're using is giving us large numbers for these two, right? And then we're going to build a bunch of other performance metrics, namely, for example, accuracy, precision, recall, F1 score, MCMC, and you name it. There are dozens of these statistics out there. But at the heart of all of them, there is this confusion matrix, right? And as I said earlier, this idea is easily generalizable to more than two classes. Let's look at an example for three class classification, and the idea is going to be the same for the 4, 5, 6 class classifications and etc. But we know that 2 class classification is what's mostly commonly used in practice. Okay, now let's say we have in actual there are 3 classes, class 1, 2, 3, and these are what the model predicts, right? Predicts 1, 2, 3. And the correct predictions are on the diagonal, right? These are what matters most, right? So this is, let's call them true positive. Basically, it's true class 1, true class 2, and true class 3, right? So the one that we call it true, they're positive, and true positive, right? So these are good numbers. We want to maximize these numbers. And what are the bad numbers? As you can guess, the false calls, right? So for example, this is what model by mistake call, so this is what model by mistake call it false class 1. In actual it is class 2, but the model by mistake is calling it class 1. So we are going to call it false class 1. So let's say this is false class 1, and this is also false class 1. In reality it was class 3, but the model predicted 1. What about this one? This is false class 2, because in reality it was class 1, the model predicted class 2. Same story for this one, false class 2, and finally we have false class 3 and false class 3. So in reality it was 1, but the model predicted 3, so it's false. This one in reality was 2, the model predicted 3. Again, this is false. So we have 2 false calls here. 2 false calls here for class 2 and 2 false calls for class 3. And the ones on the diagonal are the correct calls. We want to maximize them and minimize off-diagonal number. So as you can guess, we can easily expand this idea to 4 class classification, 5 class classifications, and etc. Now with that, let's go and review some of the most performance metrics that is used for classification, 2 class classification. All right. Let's start with the most intuitive metrics, performance metrics that we can think of, right? We have 4 numbers. We know 2 of them are good, true negative, true positive, and 2 of them are bad, false positive, false negative. The false one are the misclassifications, right? So the first metric that we're going to look at is what's called accuracy. And not surprisingly, the accuracy is defined as good numbers, true negative plus true positive, divided by all the observations. So everything, true negative, true positive, false negative, and false positive. So if I want to give you an example, imagine there are 100 predictions, 100 observations for target variable, and then 80 of them are correctly predicted, and 20 of them are misclassified. So what is the accuracy? It's 80 divided by 100, 80%, right? So what is the error rate? So error rate is going to be defined as, so let me write it down. So this is our error rate. It's defined as 1 minus accuracy. So if accuracy is 80%, error rate is 20%. If accuracy is 70%, error rate is 30%. And I guess it's easy to see that it's going to be something like, false positive plus false negative divided by all the observations, right? So we have true negative, true positive, false positive, and false negative. All right, so accuracy or error rate are going to be good performance metrics if the data set is balanced or relatively balanced. So what does that mean? It means that, for example, if you have 50%, 50-50, or 60-40, or even 30-70 observations, 30% is negative, 70% is positive, and etc., right? So if the data is balanced or relatively balanced, we can trust these performance metrics, right, like accuracy and error rate. But what if the data is highly imbalanced? So what does that mean? Let me give you an example. Imagine you're working with the default rate on credit card applications, or sorry, on credit card themselves, and we know that usually the default rates in the entire population is less than a couple of percentage, right? So if you have thousands of people holding credit cards, maybe 2% of them are defaulting, or even less than that, maybe 1.5%, right? Now imagine we have 100 people, right? 100 observations, and only 2 of them default at the end of the day in the real data. So 2% of the data is going to be default, let's say class 1. 98% of them are going to be non-default, class 0. Now, with that information, if I tell you that, okay, we have a model that the model always predict no default, right? So this is a random model, and no matter what, the model is going to predict no default. So what is the accuracy of that model? Can you think about it? So you have a model that always predict not default. So what's the outcome? The outcome is going to be 100 no default, right? Whatever it is, the answer is no default. So what's the accuracy? 98%, right? Because we know that in the real data, 98% did not default, and your model always predicted that no default. So the accuracy is going to be 98%, and the error rate is going to be only 2%. But is this a good model? Of course not, right? Because we know that the model was randomly and always selecting no default, predicting no default. So this is not a good model. So what can we say about accuracy or error rate? Can we trust these numbers? The answer is no. So when the data set is imbalanced, you should not trust on accuracy and error rate. So the other metrics that we're going to use are basically, one of them is precision, the other one is recall. So let's start with precision. So what is the precision? If you look at this one, precision focus on this column, and it's defined as true positive divided by true positive and plus false positive. So basically it says that out of those predictions that the model made, right? The model called them positive. Out of those predictions that the model called positive, what percentage is accurately predicted? Does that make sense? So for example, let me give you some numbers. Let's say we have, I don't know, the 20 observations here, 80 observations here, right? So out of these 100 positive predictions that the model has, what percentage is correct, is actually correct? So it's going to be 80 divided by 100, so 80%, right? So this is what we call precision. And the other one, let me use another color, we call it recall, right? So recall is defined as, out of those observations that are actually positive, so in reality they're positive, what percentage of them is being recalled correctly by the model, right? So let me give you again the same numbers maybe here. So 20 and 80, right? So if that's the case, so we have 100 observations that are actually class 1 in the data, and the model is able to predict 80 of them, recall 80 of them, right? So the recall is going to be true positive divided by true positive and false negative. So in this example, it's going to be 80%. And as you can see, if I want to go back to our previous example, where we were talking about that credit card default and 98% of the population did not default, and the model says that always no default. So this is the example, right? Imagine we have 100 observations. We know that in reality 98 of them are no default and only 2 of them are default, and the model is always predicting no default, right? So what do we get? So the model is always predicting no default, so it means that here these numbers are going to be 0 because there's no predictions here. There's no prediction for positive, right? And if that's the case, what is the precision? The precision is going to be 0, right? What is the recall? The recall is going to be 0 either. So now if you compare recall and precision, which is 0, which is basically the disaster, right? Compared to the accuracy, which used to be 98%. So now you know that, okay, this accuracy was fake, right? This was not reliable. Precision and recall are 0 here, right? However, these numbers are not also informative, right? So what does it mean? It means that maybe we need to work with yet another performance metrics when the data is imbalanced, right? So let me conclude these two, and then we're going to talk about the other performance metrics. So while recall expressed the ability to find all the relevant instances in a data set, precision expressed the proportion of the data points that our model says was relevant, that the model says was relevant were actually relevant, right? So among those that the model predicted that to be correct, what percentage was actually correct? Okay. Now, the third, the fourth statistics that we're going to look into is what's called F1 score. And this is very useful because it uses a harmonic mean of precision and recall. So this is precision, this is recall, right? And it's going to use a harmonic mean. Why this is better than a simple average? Because if either precision or recall is very small, the F1 score is going to be small. So for imbalanced data set, F1 score is a number that's mostly trusted, and we're going to report that number later on if the data set is imbalanced, right? Let me give you an example that why this harmonic mean is better. Let's say precision is 60% and recall is almost 0, right? If I take a simple average, the simple average is going to be what? This is going to be 30%, right? So 30% is the simple average between precision and recall. However, we know that this model is not necessarily a good one, especially if you're trying to avoid too many false negatives. You know that recall of 0 is a disaster, right? So we're going to report F1 score. F1 is a harmonic mean. So harmonic mean between P and R is what? 2 multiply 0.6 multiply 0 divided by 0.6. So we're going to get 0. So the F1 score is going to be 0. So that's why in general we're going to report F1 score instead of accuracy or even precision and recall when the data set is imbalanced. So lastly, let me conclude this slide by introducing you to what's called MMC, Matthews correlation coefficient. So MMC is yet another performance metrics. So it's called Matthews correlation coefficient, and it is commonly used for many applications as well. And the reason is that it's one of the most successful performance metrics is that it's going to use all the 4 numbers, these 4 numbers: true negative, false positive, true positive, and false negative. So far for precision recall and F1 score, we haven't used true negative, right? So maybe this is a downside of these 3 statistics. MMC is going to use them as well, right? So the formula for MMC is something like this. It's going to take into account all of those things, right? So it has true positive multiply true negative. So basically the good numbers multiply each other minus the bad numbers multiply each other, false positive and false negative, divided by the square root of a combination of the pairwise summation, right? So we have true positive plus false positive multiply true positive plus false negative multiply true negative plus false positive, and finally multiply by true negative and false negative. And as you can see in the denominator, we have something as straightforward as this, right? We are adding these things 1, 2, 3, and 4, multiply them by each other and take the square root. As you can see, this MMC maybe is a very good statistics in terms of that if the data is balanced or imbalanced, or we are also using all the numbers, right? All the 4 numbers in this confusion matrix. In accuracy, we were using those numbers as well, but we were not taking into account that the data set maybe is imbalanced, and we get misleading numbers out of it. All right. Okay, I thought that maybe I should talk about MCC, Matthews correlation coefficient, on a separate slide. So here you go. So this is our confusion matrix on the right, and this is what how we construct the MCC, Matthews correlation coefficient. At the end of the day, it's nothing but the correlation, some sort of correlation between actuals versus predictions, right? And we said that it is taken into account all the good numbers, right? All the numbers, good and bad. Right, so here on the numerator, we have true negative multiply true positives minus false positive multiply false negative, and divided by, so square root of true positive false positive, right? So true positive false positive multiply true positive false negative, so true positive false negative multiply true negative false positive, true negative false positive, this one, and then finally true negative false negative, this one, right? So what is this MCC? An interesting performance metrics, right? So we know that accuracy and error rates are misleading at the very least for imbalanced data set. Always remember of that the example that we talked about, right? 98% always no default, and the accuracy is 98%, so which is completely misleading. On the other hand, precision, recall, or even F1 score, it will not take into account the true negatives, the TNs, the true negative. These are the numbers that we're interested in, right? So for that reason, MCC is going to be maybe our best performance metrics because it's going to handle the imbalanced data very well, and at the same time, it's taking into account all the numbers on the confusion matrix for 2-class classification, right? So that's why MCC is one of the most informative metrics for any binary classifiers. So what are the output looks like for MCC? The MCC returns a value between -1 and 1. So +1 represent a perfect prediction. So this is perfect prediction if it is +1. 0 represents no better than a random prediction. And -1 is a total disaster, it's total misclassification, right? And as you can see, it's kind of correlation, right? So that's why we say it's Matthew's correlation coefficient, right? Now, let me quickly review the previous example that we had. We said that we should not trust on accuracy, rely on accuracy. So what was the example? Let me just erase these things. We said, okay, we have 100 observations and 98 of them are no default, so false negative is no default, and only 2 of them are going to be, sorry, the other way around, right? So 98 of them in reality they don't default, and 2 of them in reality they default, and the model always predict no default, right? So as you can see, these numbers are going to be 0. So here, if we calculate, and imagine our model is just so the model f hat is always 0, always. We know that this is a very bad model, or not necessarily a good model. So the accuracy is going to be what? Accuracy is going to be 98%. Precision is 0. Recall is 0. F1 score is also 0. But so these numbers are not informative. We cannot interpret them that much. We know that they are not good numbers. So this is at the very least, they're better than accuracy. But this, if you calculate the MCC is going to be what? These two numbers multiply each other minus these two numbers. So it's going to be 0 divided by something, whatever it is, we're going to get 0, right? And now we can interpret this 0. 0 means that the model that you have on your hand, it's no better than a random prediction. So this is more informative than either the F1 score. So for that reason, MCC is one of the most informative metrics for binary classifications. All right, now let's talk about ROC and area under the curve. All right, what are the ROCs, or receiver operating characteristics? Well, don't worry about the name, honestly. I don't know why we're still using that name. But the method was originally developed for operators of military radar receivers back in 1941, right? So just don't think about the ROC itself, the receiver operating characteristics. See what this performance metrics is trying to tell us. So the first important thing is that the ROC and next one, which is AUC, area under the curve of ROC, are basically used for probabilistic models, right? For the classifiers that are good, the output for those classifiers are some probabilities, like logistic regression, right? In logistic regression, the output is a probability, and then we come with a threshold. We say, okay, if the probability is greater than 50%, call it class 1. If it is less than 50%, call it class 0, right? So what are other models with probabilities? For example, KNN. In KNN, the outcome is probability. In logistic regression is probability. Later on, we're going to go over these classifiers, and we will see that which one is the output is probability or which one is not. So for example, SVM, the output is not probability. So this means that we cannot report ROC for the SVM outputs, right? All right, now let's see. In order to be able to define ROC, we have to talk about introduce two more names, which is false positive rate and true positive rate. So what are these two? So as you can see, false positive rate is, it says that among those that were actually negative, right? So what percentage of them was false positive, right? Was false positively reported. So it's called false positive rate. False positive divided by those that were actually 0. So this is false positive rate, and true positive rate is among those that were actually positive, what percentage of them by the model was correctly predicted. Does this ring a bell? We have seen this guy before, right? This is our recall. So recall is basically the same name. Well, true positive rate is the same as recall, right? So let's here call it true positive rate. And then we can plot false positive rate versus true positive rate, right? So this is our false positive rate versus true positive rate. And remember, these numbers will be reported only for models that the outputs are probabilities. So let me see. Let me tell you what do I mean by that. Imagine this is a threshold, right? So this is a threshold that you're talking about, right? So it can be 50%, it can be 30%, it can be 80%, right? At the end of the day, the model is going to give you some probability. So it says that for this individual, the model predicts that the probability of default is 80%. Then, if the threshold is 50%, we're going to call it 1, and anything above 50% 1, anything below 50% 0, right? We can play around with this threshold, right? Why using 50%? Why not using 30%? Why not using 70%? That depends on the context of the research question that you're dealing with, right? So let's say, why do we ever care or why do we ever want to reduce this threshold? So here's an example, COVID test result, right? In order to avoid too many false negatives, you're going to reduce that threshold. You don't want to send out so many patients out there that are false negative, right? You don't want to jeopardize the society. So in that case, you're going to reduce the threshold. If you reduce the threshold to be more conservative, you do it to reduce the false negatives, right? And now in this equation, if I reduce the false negative, what will happen? If I reduce the false negative, the true positive rate is going to increase. So this is a direction if the threshold decrease, right? So if the threshold decrease, then the true positive rate is going to increase. From the other hand, what if you want to increase the threshold? So what's the example? Spam detection, right? You want to be more conservative. You want to make sure that you're avoiding too many false positives, right? So for example, if an email of your friend does not necessarily go to your spam or junk box because your threshold was low. So you want to say that, okay, if you're 90% sure, if you're 80% sure that that email is spam, let's label it as a spam, right? So we do that, we increase the threshold to avoid too many false positives, right? If I reduce the false positive, then what will happen? So if false positive is reduced, as you can guess, here, because it's both shows up on numerator and denominator, so the entire thing is going to get reduced, right? So the false positive rate is going to decrease. And this is what we see here. So here, as the threshold increase, the false positive rate is going to decrease this way, right? So now, based on different values of threshold, we can calculate different false positive rates and true positive rates. And ROC is basically the curve that summarizes all these numbers for us, right? So if the threshold is 0, what are the answers? If the threshold is 0.1, what are the answers? True positive rate, false positive rate. If the threshold is 0.2, and etc., etc. So let me show you the extreme cases, and then you can think of any numbers in between, right? So here, this one is basically when the threshold is exactly equal to 1, right? Because we know that as we go from right to left, the threshold is increasing, and as we go from up to down, the threshold is also increasing. So here is the maximum threshold, right? So if the threshold is 1, what does it mean? It means that you're too conservative. You're basically telling the model that if the probability of, let's say, positive is greater than 100%, then label it as positive. So basically, whatever the model does, we're going to say that it's going to always predict negative, right? Because it doesn't matter what are the numbers, you're too conservative. So the confusion matrix is going to look like something like this. So here, the model always predict that, again, whatever the model says, the positive is going to be 0, right? So here, I don't know, I'm making up some numbers. Let's say we have 65, 35. And if that's the case, what's the true positive rate? So the true positive rate is going to be 0 because it's 0 divided by 0 plus 35. The false positive rate is going to be also 0. So we are here, 0, 0. So when the threshold is 1, we are at the point 0, 0. When the threshold is 0, we are here. So here is when the threshold is 0. And this basically means that whatever the model predicts, let's say 20%, 30%, 80%, whatever it is, because the threshold is 0, we're going to always call it positive. So this is how the confusion metric is going to look like. Again, whatever it is, it's positive. Let's say 40, 60. This is going to be 0. Again, false positive rate is going to be 40 divided by 40, 1. true positive rate, 60 divided by 61. So we are at 0.1 and 1. Right? Now, anything in between is going to be summarized by our ROC curve. So the ROC curve is going to summarize all that values for true positive rate and false positive rates for based on different threshold level. So I just emphasize it one more time. These ROC is reportable only for the probabilistic models. It means that the models that the outcomes are probability, and we have to come up with a threshold to make it a classifier. All right, and lastly here on the diagonal, this is what we call no skill or random classifier. So basically, if the model is always predicting 1, always predicting 0, or basically randomly doing that, it's going to always lie on this 45-degree line. So hopefully the model that we're working with, the ROC curve, is something on top of that no skill line, right? So this is our no skill line. So this is a relatively better model. This is better model, moderately better. This is the perfect classifier, right? This doesn't happen in reality. So, but this is perfect classifier. And yeah, that's pretty much it. Now, instead of judging that if, for example, this model is better or this model, or when these things are very close to each other, instead of looking at it visually, which we don't have the luxury to do that all the time, so let's summarize all these things in one number and calculate the area under the curve. All right, so this is what we call area under the curve. So basically the area under the curve is going to summarize the numbers for ROC in one number, right? The area under the curve, technically it's defined as the probability that the classifier will rank a random chosen, let's say, plus examples higher than a negative examples. Naively speaking, we can think of it as probability that the classifier is able to distinguish classes, right? So if the AUC area under the curve is 40%, it is bad because it's doing worse than a no skill, worse than a just random selection. The AUC for a no skill model or random model is going to be 50%. So anything above 50% is good, anything below 50% is a disaster, right? So this is a good model, this is a better model, right? So 85% is basically, it says that it's better than random. So you have a model on hand which is doing something better than a random, right? And lastly, I just want you to remember that area under the curve is a scale invariant. So basically on the other hand, it's threshold invariant as well. So it works for all the thresholds regardless of what you use for the threshold. Basically, it's summarizing all those numbers for you. All right, so that's pretty much it. This is performance metrics for classification in machine learning. Until the next one, take care.